Okay, to begin with, we're talking about the CAN lab, and then we're going to take a brief break from it and do some review. But I want you to just get your subconscious working on this. Let's say that we measured the height of a can, and it was 100 centimeters. That's pretty darn big, but let's say it was. That is a meter tall. Okay, that's ridiculously large. Let's go with 15 centimeters. Okay, and the radius was, let's say, 10. When I did the height, no, the radius 10. That's a huge. Well, maybe that's what it was. Okay, the height being 15 divided by 10. 15 divided by 10 would equal 1.5, right? That would be a typical scenario, except your numbers, of course, are going to be used in the real world. We're going to actually take real cans here and measure them and stuff and put the data into the chart. And you'll get a whole bunch, and also this is really important. Which one was it? Like this was the Del Monte or whatever the brand is, okay? So what we're trying to do is figure out if these ratios that you see on these cans, the height to radius ratio, is actually maximizing the volume of the cans or not. All right, so if we're going to do this with volume and surface area, those are the two things, right? They have to hold a certain amount of soup or whatever it is, and we want to have their surface area be small. Why don't you write down the two formulas that you know of for cylinders like this, cans, okay? One's volume, and one is surface area. If you haven't got them memorized, I will be telling them to you in a moment, but try to write them from memory. We did talk about them on Friday. I'll pause for a second. Okay. Pi r squared is a good start. That's the circle on the can. What am I not factoring in yet? Height. Pi r squared times height. Surface area, the area of all the surfaces on a can. Would you agree there are two circles and hence 2 pi r squared? Plus there's the other part, the part that goes around the can here. Around the, if I peel it open, the can would look like this and would have the top and the bottom like this, and then there'd be that big middle part, which is actually a rectangle. Who can finish off that formula? Yes. Yeah, but we know them in terms of r and h. 2 pi r squared plus, it is the circumference. This is the circumference times the height, but the circumference we know in terms of 2 pi r. So this one's circumference is 2 pi r, and the height, so 2 pi r h. 2 pi r squared plus 2 pi r h. All right, good. We've got our two formulas. Now, do you remember that in the past, I suggested that we take a picture of our thing, our situation, and we take and we label that picture really thoroughly, but we may as well, in this case, instead of labeling it really thoroughly, radius is going to be radius, height's going to be height, and the volume is pi r squared h, I could put that on the inside. Volume is pi r squared h. But really, that's just kind of cheating to make it fit my scenario, which is draw a picture, have a formula, stick the stuff from the picture in the formula. But basically, I got to get this stuff into here. The little formula needs to go into the big formula. Do you see any volume in the big formula? No. And therefore, we need to solve that. Did you notice on the front side what we said the volume was going to be? 1,000. We are going to standardize that. If we don't hold that volume constant, then you're grabbing around trying to find the best surface area for what? You have to know how much you need to hold. Okay, so we got to have a number for that. So we picked 1,000. So now I'm going to change this formula to 1,000 equals pi r squared h. Now do you get that you could either solve for r or for h and then put it into that bigger formula? How do we solve this little formula right here for something? What would be the easy thing to solve for, r or h? H is the easy one. Because r is hard to solve for because at the end we're going to have to do what? A square root. And that's a pain in the butt to put a square root into a fraction, into this other big complicated one down here. But anyway, so if I'm going to solve for h, how do I start solving for h? Divide by what? By r squared. That cancels that. And the height is 100 over pi r squared. Sorry, 1,000 over pi r squared. So then there's only one h in this whole formula. It's right there. You could drop that in. Now we have made one big formula to rule them all. Surface area is 2 pi r squared plus 2 pi r, 1,000 over pi r squared. All right, now I want to warn you, the graphing calculator is the only way you would find the lowest spot on this graph. Like, where does this the lowest it ever would be? You're definitely going to want to graph it and find the lowest spot. So I want to warn you what this looks like. Everybody, when they first graph it, they think it looks like this, like one of these kind of 1 over x kind of graphs. And I want you to think about why that would be. Why would it look like a fraction function? Yes? Nope. The reason there's a fraction function look to it, you know, like 1 over x, it looks a little bit like 1 over x. Do you agree that that graph I kind of sketched out there looks a little like 1 over x? Because there's a fraction involved. See, it's right there. That's the fraction. Do you remember that the asymptotes are the horizontal asymptotes are the ones where Bob tells you? Is this one bigger on bottom, bigger on top, or same on both? Come on, just the part I put in the box in. Bigger on the bottom. Okay, that's the part that has the fraction. That's a Bob. And therefore, the horizontal asymptotes is the outside. That's the horizontal asymptote. So the point is, you don't have a normal asymptote that runs like this. You might think you do, but you have a weird asymptote for that. So when you zoom out on your graph, it's one of the weirder times graphing-wise for your life. You're going to like, this is going to blow your mind. You think it looks like that, but then it doesn't at all. When you blow and you zoom out on this thing, it actually looks like that. But see, you were zoomed in only to this area and to where it was only going down, and you couldn't see it before. But anyway, when you're done, your graph has a slant asymptote. Why does it have a slant asymptote on it? Because of this. And then you want surface area versus radius. Do you get that this spot right here has the least amount of surface area? The red dot I put there has the lowest amount of surface area. So that's what you have to find. And what will it be? It'll be a radius. And let's say that this is at, let's say that that's at 7. Then you have just figured out, for having a volume of 1,000, you're going to want a radius of 7. Wow. I'm not saying the answer is 7. You have to figure out the answer by graphing it. If you haven't already written out this big equation, I wasn't doing this just like because I love equations. I was helping you with your CAN lab. If you haven't already written that down, you better hurry up and write it down because it's not going to be up there much longer. Then you're going to type that puppy in, and I'm warning you, when you type it into the calculator, a lot of kids had it not work until they put parentheses around that. And last thing I'm going to tell you is that your window, as you graph this thing, you're going to want x equals, so x max to be like 50, and the y max to be 1,000, because remember we had the surface area of 1,000 is our kind of our goal. So make your X max 50. Sorry, couldn't even read my own writing up there. X max 50. Y max about 1,000. And if you do that, your graph will look like this, and you'll see the slant asymptote really well. Have you written that down? Because it's going to be off the board in a few seconds here. Yes? Think about this. Do you really need to see 50 units in this direction? Do you really need to see 50 units in that direction? So I'll let you choose those based on being smart. Okay. Now let's say you figured out the radius is 7. Do you get this little formula right here has radius and height in it? And if I know the radius is like 7, and I know the volume is 1,000, do you get I could figure out the height really easily if I knew the radius? You can just solve for that. It'll be super easy to get the height. So get the radius off the calculator and then get the height based on this. Then your radius equals like 7. Your height equals like 21. Do you get the ratio there if you're taking height to radius? It would be 21 over 7 and therefore 3.0. I'm not saying that that's the right answer, but that's what you're trying to go for, is trying to find that ideal ratio of height to radius. I totally made up this 7 number. I totally made up this height number. You have to find this radius of whatever it is off of your graph. All right. I want to give you a few minutes to work on that. And when you're, I know you'll have some questions about it. And then when you kind of like, okay, my brain is fried and I need to do something else, we are going to have the cans. Everybody that brought cans in, have it out on your desk. If you stored it in the back thing, awesome, go get it and get a ruler. And I want every can to have a ruler sitting next to it. And I want you to go around the room and measure 4, minimum 4, maximum 5 different shaped cans. Don't get all the same kind of can. And you're going to put that data into your iPad, into the lab right in here. All right, you have a bunch of time to work on this. I know you're going to have more questions. I hope you took good notes, because I won't be repeating everything for you just because you didn't want to listen the first time. All right, we'll be back in a minute. We'll do some review when we do. Okay, so here is a summary. By now, you have figured out the purpose of this lab was to figure out what is the ratio of the ideal can when it comes to its height versus its radius. And we did an example of one with 1,000, and we knew the volume was 1,000. Please don't talk right now. And on that volume of 1,000 can, I hope your radius came out to like around 5-ish. And then you'll have to just, that's easy to solve this equation then to find the height. And then you just have your height to radius ratio. And let's say that your height to radius ratio comes out to a 2.5. Then you'll know that any can that has 2.5 radius that you found before was the perfect can. There's only one perfect can in the room as far as I know. Most of the cans, maybe most of the cans were running like a 1.5 and you were at a 2.5 was what was perfect. Then you got to figure out what's too big about them. Is their height too big or is their radius too big to be the perfect can? Okay. Then you're going to summarize what you did in words here. You're going to actually show me the work that you did with your calculations, like solving the equation. And then last, you're going to have some reflection like about, looks like the average can is, you know, they make them too wide. Otherwise, they could be closer to the ideal surface area. All right, enough of that. Now we need to do a little bit of review for the test that you're going to have. And there's a few topics that we covered on that you're going to want to review with me. So be prepared to do some practice problems. This is the part where if I see you typing in your calculator, that would be a very bad thing because I need you with me. All right. So here is an equation, x squared plus 3x plus 2 over x squared minus 1. And I'm going to say it's f of x. We have learned, first of all, if you can factor it, you should. And if you need to find the roots The zeros, the x-intercepts are where what? Y equals 0. And last, if you need those x-intercepts, those roots, you can factor it, you should. If you can't factor it, quadratic formula. Okay, good. So now, I'm going to ask you a bunch of questions about this one right here, and hopefully you're already factoring it, because you know that that would be important. And then I'd like you to tell me its domain, as in all real numbers work except what? And then I'd like you, the things that don't work, the things that break your function, the things that are not in its domain, are usually either asymptotes, vertical asymptotes, or they are holes. So if there is any hole here, tell me where it is. If there's any vertical asymptote, those are all about the base. And the last thing is the horizontal asymptotes, which are the ones that Bob can tell you about. And then after that, I'd like you to tell me the x-intercepts. Remember, that's where y is 0. And then the y-intercept. Try those, and I will give you some help with it in a moment. Yes, clarifying question?
The hole, do we have to show the y value?
Good question. And the ideal student should be able to tell me the hole. X is, let's say, 5. You think 5 is what creates the hole? Then you should be able to say it's 5, 1/6 or whatever the coordinates of where the hole should be. But if you have it to this level, that might be good enough. Kind of depends on how the question is worded. But try to figure out both parts. Try to do it like this, where you can tell me the x and the y of the hole. It's not too hard. You just stick the x in to the equation after you canceled some stuff. All right. I'm going to pause for a second while you give that one a shot. Okay, I need to get started. So domain, all real numbers work except what? I like to make these as the number line. And everything works except, well, the only things that will make this die or this crash is if the bottom crashes, as in the bottom becomes a 0. X plus 1, x minus 1 on the bottom. On the top, x plus 2 and x plus 1. So if I'm talking about the domain, I'm looking down here and seeing -1 and +1 are going to be problems. So I put in -1 and +1 and say, can't be -1, can't be +1. Raise your hand if you had your domain right. Okay, good. The verticals. The verticals are all about the base. Do you get that the things on the bottom here are either holes or asymptotes? That's why they cause the function not to work. It doesn't work here and it doesn't work there because there's either holes or asymptotes there. So which one of the two is a hole? The x equals 1 or the x equals -1? It's -1 that creates the hole. See, when I cancel these two off, these are the two that were the same, right? So -1 is the thing that causes the hole. X equals -1. Now I said it would be best if you were able to tell me where it was. -1 comma what? So then I want to put the -1 in the remaining function here. Put a -1 here, put a -1 there. That becomes 1 over that becomes -2. 1 over -2 looks like this, -1/2. -1 comma -1/2. That's where the hole would have been on the graph. That's where the graph got interrupted. Yes? I said you had to be prepared to give me this answer. So if you can't give me that answer, it would be wrong. But, you know, really, you're asking that. It's actually a lot easier to just learn how to do it. All you got to do is take this number, stick it in the equation. It's not that hard. If you stick it in the original equation just crashes. So don't do that. Stick it into the other equation. The one after you canceled this, that's the equation you use. The one after the thing got canceled. Okay, moving on. Horizontals. Bob tells us the horizontals. And is this a bigger on bottom, bigger on top, or same on both? Same on both, and therefore the lead coefficient is what it's all about. Oh, that's not a 2. What am I thinking here? That's a 1, and therefore it's 1 over 1, y equals 1. Oh, verticals. I skipped that one over. The verticals are the things on the bottom that weren't holes. So the one that I see that's left is this guy. He didn't cancel. So x equals 1 is a vertical asymptote. And last but not least, the x-intercept and the y-intercept. The x-intercept is where y is 0. Here's where y goes. That's 0. So we need the top to be 0. If you want the overall answer to be 0 in a fraction, the top has to be 0. And that factored again to x plus 1 and x plus 2. So there were two things that would make the top 0. Negative 1, x equals negative 1, and x equals negative 2. Those are the two things that would be our x-intercepts, also known as our zeros, the roots, the solutions. Yes?
It doesn't cross at negative 1. Like it's not be negative 1.
It can be negative 1. Exactly.
Oh.
All right. So where it would touch would be at negative 1, but it doesn't actually touch there because there's a hole there. All right. Anyway, and on to the last piece, which is the y-intercepts. The y-intercepts are where x is 0. Just have to stick in a 0 here, and here, and here, and you get 2 divided by negative 1, which makes negative 2. Y is negative 2. Or if you want to say the y-intercept is where x is 0, it's 0 comma negative 2. That would have been a good answer also. Don't leave me a bald answer of negative 2. Just say negative 2 and I will mark it wrong. You got to say x is negative 2 or y is negative 2 or put it in a point format like 0 comma negative 2. All right. So last thing, sit down please. You're not leaving for another 1 minute. Last thing is those kind of problems that have to do with rates. There were some kids making sandwiches in the commons the other day, and one kid could make 5 sandwiches in 3 minutes. Another kid made like, let's say, 8 sandwiches in 5 minutes. Then how could I do a problem where I said, I got to get somebody to make 20 sandwiches for me? So I get Bob and Sally together, and I have them both making sandwiches until they make, how many did I say I wanted? 20. Well, then you'd go the rate plus the rate equals the rate. 5 over 3 plus 8 over 5 would equal, and these are sandwiches, and these are mins. Where do I put the last number? If I have 20 sandwiches, the only logical place is on the top. And then what don't I know? I don't know how long it's going to take. So remember, these are rate plus the other rate equals the combo rate. The rate questions are important. Any questions, clarifying questions on that? All right. So that's our last for today. Your only homework I'm sending you home with is write up that lab. It's a good word, real world word problem. That's all I have for you for today.